Hi, welcome back. So this part is actually about deep learning. So it's an intro to deep learning. As I mentioned earlier, in the earlier video, deep learning is actually using a very complex artificial neural networks. So it's 10 or more hidden layers. But what's the advantages and how is it related to machine learning? So these three terms have often been used in the media. So this diagram actually just shows you the relationship between the three. Artificial intelligence, as we talked about in the beginning, is actually the overall area. It's the broader area, and it actually has a long history all the way back to the 1950s, right? So artificial intelligence basically is this idea that we can create machines or programs that can mimic the intelligent human behavior that we see uh, when humans are able to do certain things that actually make them that deems them as intelligent. So there are different approaches. One of them basically is to have a rule-based approach. So you do not need to actually learn from any data. All you need to do is have to ask the human expert to try to explain what the rules are to do something. And if you're able to mimic that similar intelligent behavior of the expert, therefore it's actually considered to be a intelligent, is considered to be a form of artificial intelligence. So these are some of the early successes, but there was a problem, and there are many problems actually where the rules do not exist or the experts are not able to explain to the programmer what the rules to be used are. So one of the early examples of this kind of problem is actually the email spam problem. So email spam, uh, initially people tried to come up with rules for the keywords to use to detect spam. However, this proved to be really largely unsustainable because the spammers keep coming up with new and new spam words. And human experts are just not able to keep up with all these new spam, come up with new rules to actually keep up with all this new spam email. So some bright spark actually came along and said that instead of a human trying to learn the rules to be used for detecting spam, why not we try to learn the words or the spam words themselves from the data. And hence, actually, this is actually the start of one of the very successful applications of machine learning, where machine learning is basically learning the rules from the data itself rather than asking a human expert what the rules are. So this actually helped to solve that problem of email spam to a large extent. So these days, actually, you will not receive as much spam anymore. In fact, most of the spam prevention engines, they are quite good and they are quite adaptive in learning new spam patterns as the data evolves. Right, but the thing is that for machine learning, at least the traditional machine learning, they were very good for structured data which actually falls very neatly into rows and columns, what you will find in a spreadsheet or a database table or any structured document that you have of the data. It could be a flat file where the data are just separated by commas. So if you have this kind of structured data, the traditional machine learning techniques, they can work very well, just like the problem of the spam detection. However, the moment you have actually very high dimensional data or very unstructured data, unstructured rather than structured, data that cannot be easily divided into rows and columns in the spreadsheet, then the traditional machine learning or the classic machine learning algorithms like decision trees, they don't work very well. What do I mean by unstructured data? Think about data that comes from an image. If you take a photo with your smartphone, the number of pixels or the dots, the colored dots in the picture could run into millions. Just a simple smartphone, low-end smartphone will run into millions of pixels today. And if it's a higher end one, it can be even 4 million pixels or 4K resolution. So if we try to fit that image or pixels into a Excel spreadsheet, every single dot will basically be one column in the spreadsheet or one dimension in the data. So you can imagine a spreadsheet where there are 1 million columns or 4 million columns. It's really too unwieldy for you to actually use that kind of data using the classic or machine learning approaches. So this high dimensional data or unstructured data, they don't fit very well within the kind of algorithms that flourished in the 80s and even late into 2000. So the new technique using machine learning called deep learning, a new technique using very many layers of hidden layers in the artificial neural network. And this was called deep learning because it's very deep, right? There are many, many hidden layers in the artificial neural network. They work very well with this kind of data, unstructured data. And this actually was the bugbear of machine learning scientists, right? For a long time, they couldn't actually solve this problem. But along in the late 2010s, actually, these techniques arise for two reasons. One is because there was a problem. We couldn't deal with all this unstructured data and images and sound bites and even very large bodies of text like email, social media data. These are basically considered unstructured data because it cannot fit it easily into rows and columns in a spreadsheet, right? For sound, it's just a continuous waveform and there are many, many samples per second. Just like images, there are many, many pixels in the whole image. For a large body of text, the text that you have in your social media or in your email or in your documents, they don't have a particular format. The words can occur in any order or sentences can occur in any order. So that kind of text, naturally flowing text data is also considered another form of unstructured data, right? So this is actually treatment text, large bodies of text, sound, and images as well as video, unstructured data. They couldn't be solved with the traditional machine learning techniques. Now, deep learning didn't just arise because there was no theory behind it. Actually, some of the theory for artificial neural networks dates all the way back to the beginning of the machine learning period. But the processing power that was available in the early days just wasn't sufficient to actually process many multiples of hidden layers. Just not enough computational power to make it practical. For example, one of the early deep learning pioneers, he invented his algorithm back in the late 80s, but it would take him days to actually do the training because the computational power available in those days just wasn't sufficient. So this is one aspect. The other aspect really is that there's really a lot more unstructured data today in the internet era, where you have Instagram, you have social media, and you have video cameras, lots of IoT devices that also capture images. So there's a really pressing need to actually handle this unstructured data that is actually growing more and more. And with the increasing computational power that's actually available today, it's actually sufficient to actually make these techniques of deep learning actually practical because you can do the training in minutes rather than in days now. So there's two particular things that are special about deep learning. So deep learning is actually a subfield of machine learning, as mentioned earlier. And so AI is the bigger area, smaller area is machine learning. And within machine learning, we have one type of machine learning, which is basically deep learning that uses artificial neural networks and works very well to learn from data that's actually unstructured. So there are two key characteristics. One is that actually, when we use deep learning, it's able to form multiple layers of abstraction or representation of the data. In fact, deep learning is called learning representations in a more formal context, right? So we will find that there's an international conference of learning representations, but there's no international conference of deep learning per se. So this learning representation is very much like how we would actually recognize anything. If I'm trying to recognize an image of a face of a cat, for example, I would not be just recognizing the individual dots in the cat's image. What I'll be recognizing is certain characteristics. For example, there's this round object, which is the face. Then there's these pointy triangles that are on top of the face called the ears. And then there's this triangle in the center of the face that's actually the nose of the cat. And then there are ovals on either side of the triangle that of the nose that actually are the eyes. So these layers of abstraction actually help me understand that this image that I see is actually a cat. I don't actually just look at the individual pixels in the image. And the layers of abstraction, actually there's a hierarchy to it. Certain abstractions are more basic. For example, the face. If the face is missing and you just have the cat ears and nose and eyes floating in space, then it's very likely that it's not really a cat that you are seeing, but it's maybe some sort of phantom, right, or ghost that you're seeing. It's not a real cat, right? Because without the face, which is the holding thing for everything else, and that's missing. That's actually a very low level of abstraction that's actually missing. So a very basic level is missing. The higher things, even though they're present, they are not likely to be it's not likely to be what you're targeting, right? Which is the cat. Now, if the higher level representation, maybe part of the ear is obscured, like the earlier photo, right? A blanket covering the cat ears. Even by the face and the other features that you will still recognize it as 98% cat, right? Just because one ear is not visible, it doesn't mean that it's not a cat. So we actually do this all the time when we're trying to recognize pictures. We do not look at things at the same level, that we actually form different levels of abstraction in our mind as we try to recognize that object. Same for language. If we are talking about a language, there's always letters. The letters form into words. The words form into sentences. The sentences form into paragraphs, and the paragraphs form into sections, right? So there's this hierarchy of different levels of complexity or representation that actually conveys meaning. This is something, is a particularly human trait, and you will, what we do automatically is in our brain, we try to mimic the same layering of the different hierarchies of representation in deep learning. So this one distinguishing characteristic. Right, so deep learning methods aim at learning the feature hierarchies from features from higher levels of hierarchy to formed by combining lower levels. So the sentences are formed from words, words are formed from letters. Okay, the lower levels actually are built up, combined together to form the higher levels of more abstract representations. Automatically learning these features at multiple levels of abstraction allows the system to learn complex functions of mapping from the input to output directly from the data without depending on human crafted features. Now, what this actually means is that traditional machine learning techniques, when we try to handle unstructured data, like this image of a car, we actually need a human engineer to come in to sort of write a handcrafted feature extractor. So this thing will basically detect certain patterns in the data. For example, there are presence of wheels, so you scan the picture for the presence of wheels. You may be able to detect the windows or the rectangular objects at the top, scan for these features, and then basically just extract each of this into whether yes, it's present or no, it's not present. Are there wheels? Yes. Are there windows? Yes. Is the color yellow? Yes. These are all the individual features extracted, but you need a human to actually craft that feature extractor, the thing that actually determines the properties, because the computer algorithm, like a standard classical classifier algorithm, is not able to actually extract those features automatically itself. Now, these features may also be at different levels. So, for example, low-level features will be the presence of the wheels and the windows, but a mid-level feature will be that the wheels are actually below the windows, right? There's a relative position. The windows of the car must be above the wheels. So that's a mid-level feature. A higher-level feature that actually detects the relative positions of the two objects. Again, you need a human to come in and actually write out the handcraft, the mid-level extractor, right? So detect the two lower features, and then detect also the relative position of two level features. But deep learning is different from this. You can notice that actually the part that is actually done by machine learning, that means autonomously or automatically learning from the data itself, is all the way, right? It's no human involved. The low-level features are learned automatically, the mid-level features are learned automatically, the higher-level features are learned automatically, and obviously the classification end, after the features are extracted, is going to be operating automatically as well. So end to end, right? The hierarchies are hierarchical and it's actually automatically trained. What you need is just lots and lots of computational power, and also lots and lots of data to actually do the training. Another way to look at it is this. Okay, we have the input. In the past, we need a human to extract all the key properties or features, and then we pass it through a standard, maybe simple neural network, a standard classification algorithm, and we get an output of yes, it's a car, or not, it's not a car. But with deep learning, the human is out of the loop. There's no need for handcrafted features. Everything is just done directly from the image, and the output itself is end-to-end training. The feature extraction and the classification section, they are actually distinct sections. The first part of the deep learning network is to extract out the different hierarchies of features, and then the tail end typically it's just the standard. It's very similar to the classification algorithms that we use, where we actually have a human extracting the features. So what is actually new is the automatic feature extraction in deep learning. So the tail end is just a standard classification neural network. Right, so you can, without the need for human, it really saves a lot of effort because it's handcrafting for the features is not scalable and you got to do it different for every single use case. So for cars, it's one set of features. For motorcycle, it will be different. For even different mix of cars, it will be different. So it will be quite difficult for this to really scale up to a large scale system. Whereas for deep learning, you can do all of this automatically without having to have a human involved. So that's one aspect, that hierarchical learning representations. The other aspect of deep learning that makes it very special is the fact that it can actually scale. Most algorithms will improve the performance as more data is present, but as more and more data is present, there will be a saturation point and the performance will not improve beyond that. However, deep learning is one of those algorithms which is sort of infinite in its learning ability, right? It's just how deep it is. So the more data you present it, as long as you have sufficient computational power, it tends to be able to learn more and more and more patterns. So you can even recognize a face in China out of 4 billion in a matter of seconds. So this is an activity that I want to just take a short look at. So I'm just going to switch over to the website. So this is a demonstration of a convolutional neural network, or it's kind of a deep learning network for recognizing handwritten digits from a very famous data set, the MNIST data set. So this is a set of 60,000 handwritten digits with 10,000 test examples. The digits are basically black and white only. So it's a fairly simple database. Each image is kind of small with 28 by 28, and it has been further reduced in size to make the computations even less, because it's actually running on the browser itself. So this is actually what we call a learning curve, which actually shows the error that we observe with a different number of passes through the data in the neural network. The training passes are what we call epochs in the training of the neural network. You can find that the more epochs or the more times we pass the network, the data through the neural network, the error will keep dropping. But it will reach a point where the error will sort of taper off, so the errors don't reduce as fast. I'm just going to continue the training. So you can see that it will keep dropping and dropping. Okay, starting from, but within about 1,000 iterations, right, you can find that it has already dropped to quite a low level. These are the examples of the data that we pass through it. So this is a fairly simple neural network with just a couple of layers. So it's just showing you the visualization of different layers. So this is actually the first one, all digits being passed to it. The second layer, you can see that it's actually detecting certain shapes in the data. And for the convolution neural network, you can see that the lower level abstractions like this, right? The shape of the original digit is quite evident. You can at least see the outline of it at this level. But the next level, which is actually combinations of other shapes, this is just the activation layer. It doesn't actually change very much here because it's still the same thing, except that we apply some sort of non-linear filter to it. So you can see it becomes sharper, but the shape is still there. Then we do a compression, or what we call a pooling layer, and then there's one more layer of convolution. And as you go up, okay, beyond the first layer, then the shapes become kind of abstract. You can no longer really see the 1, 2, 3, 4 digits very clearly in the shape anymore, because it's a higher level abstraction. It's a combination of the lower level shapes like slants or round shapes combined together at a higher level. It's not so distinct, and you cannot really trace these shapes at a higher level to the original shapes of the digits anymore. At the even higher or more abstract level, it will basically be flattened out, where a white dot represents that it's more likely to be that particular output. Several combinations of this actually gives you the final output, which will just fire off the activation for the one that's most likely to be the correct digit. So here we have visualizations of the output. The green bar means that it's correctly predicted. So this is correctly predicted to be 8. The length of the bar actually indicates how certain or how strong the firing strength, right? How certain it is that that particular output is that value. So sometimes it's very certain, but it's wrong, it's red, right? So in this case, it's very certain it's actually some number, but it was actually a different number. So you can see that where is a mistake like 2 and 7, 7 and 2 are often mistaken. You will find that the digits, right, where it's wrong, the next number may be the correct one. But the one that's most certain of is actually very certain, but certainly wrong, right? She guessed wrongly, like this, right? 3 is the correct number, but you guessed it was 5 or something like that. But you can see that some of the examples are really very bad handwriting, and even as a human, you might find it very difficult. This one, right? Is it supposed to be a 3 or 2 or what? Right? It's very difficult even for a human to really be very certain what that digit is. And some people write 7 with a bar. That really tends to confuse it a bit. Some people write 7, but they don't write it straight, right? They don't have the slant, the diagonal line, so it looks like a 1 because it's actually, the whole figure is actually slanted. Similarly, 1, if you don't write it straight, but you write with a slant, you might think it's a 7 because it just didn't detect the horizontal bar. So these two, 1 and 7, they can be confused. 2 and other digits like 4, like 7 also tend to be a bit confused because of the horizontal, the slanting part, right? If you didn't detect the tail properly, you would think that it's a 7. So you can see that actually where it makes the mistakes, the human might make a mistake as well. And we can actually get the error rate to be less than 1 in 100 very quickly, because this is actually a few percent only, right? It's less than 1% very quickly. So this convolutional deep learning networks, they are very effective in actually detecting shapes in images. Okay, resuming the slides again. So that exercise just shows a simple demo. So you can actually run a neural network in the browser itself if the network is simple enough. So if you're talking about a production scale network where there are hundreds of layers or even a few tens of hidden layers, the computational power will far exceed what can run on a normal laptop, right? So you would actually need some sort of a server or a deep learning workstation to be able to do the training. But if you're running a simple, relatively simple data set like this one, which is just 28 by 28, I think the number of layers just now was something like 5 hidden layers. So 4 hidden layers actually. It's not too deep, so it will be able to run even in your browser. But you can see that even with a simple network like that, handwritten digits that can be quite difficult even for a human to recognize, it can actually do a pretty decent job of getting the accuracy up within a short number of just 1,000 iterations or epochs through the data set. So it's very effective technique for image recognition. And today, deep learning is the go-to algorithm for image classification, because the results that we get from image classification using deep learning far exceeds traditional techniques like support vector machines or doing a reduction using eigenvectors and then doing a support vector machine over that. The more traditional techniques, but the accuracy was always tapering off like 10% error, which is worse than what a human can do. But with the new techniques using deep learning, the accuracy already drops to a level that is equal to human. And these techniques were actually introduced sometime in the year 2000. So it's not that long ago that people actually started adopting the use of convolutional neural networks or deep learning networks to actually do image recognition. Just 2012. AlexNet came out, it won the ImageNet competition, and the results was a few percent better than the previous errors. Were always stuck like slightly above a 10% error. When it dropped below that, people were just astounded that, hey, this new techniques is the go-to now. And people just started refining, and within a few more years after 2012, the performance of these image recognition algorithms actually exceeds human. So it's superhuman performance. We're capable already. And they continue to become even better and better today. So this is actually as I said, the deep neural networks currently is the go-to algorithm for image recognition. And also, of course, video, which is just multiple images in time. Right, so let's talk a little bit about how we will actually build a machine learning model once we have the data, because this is actually what we call the machine learning workflow, and we'll go through a practical exercise to do this in the next set of 4 videos. But this particular last part here, just want to go through the flow with you first. Actually, the workflow or the process of building the model is quite similar whatever the tool you use, right? Whether you're using Azure Machine Learning Studio or using Google's tools or Amazon tools, the process or the workflow for building the model is very similar. So what you do is that you get the data in or data ingestion. Normally the data is not really ready in a form that you can actually do the training with. So you will actually do some data transformation or cleaning for the data. Once the data is ready, you will actually split the data into 2. One is the bulk of the data will be used for the building the model itself, to do the training, to learn the patterns in the data. That's what we call model training or building. So the bulk of the data goes to here, but we take a small number of random samples and we set it aside like final exam questions. They are test data, right? It's a quality check to make sure that whatever the model has been trained, the output actually is consistent when we apply the test data to it. It's just like giving students a final year exam. They have been trained with mock exams and they can give you a good result with the mock exam, but you can't be too sure that they have actually learned the right thing unless you give them some random questions that they have not seen before and really test their understanding, whether it's correct or not. Right? So this is a similar idea. So the bulk of the data I have clean, I'm going to use it for training so that the algorithm will learn the pattern in the data and give me the correct predictions. But just to make sure that it's actually learning the correct pattern and not overfitted or underfitted, I give it some randomly picked samples from the original data set. So these are actually blind data that's never been seen before by the model. Now, if the model is correctly trained and built, the performance or the results that we get using this test data should be similar. They might be slightly worse than the training data's predictions, but the predictions that we get with the model using the test data should have roughly the same performance as what we see in the training data. If they are very different, you probably have a problem like overfitting on your hands. Right, so that's a surefire way of signal to you that you actually have a problem with overfitting, where the test data performance very much worse than the training data performance. So model testing is just a quality check to make sure that whatever you have built at this stage, which is the trained model, the output from this stage, is ready for actual use in the application itself. Right, and once the model has been deployed, that's not the end of the story. Actually, oftentimes you need to still monitor to see that the performance continues to be consistent with more data that you receive, because if the model, if the situation change and the model needs to be retrained, hopefully this feedback loop will help you detect it. So once you detect that the performance has deviated from your original setting, you probably need to get new data, or you need to do some tweaking of your model. You need to do the retraining so that the performance is up to a reasonable standard again. Now, during the model testing, it hasn't gone to model deployment because you detected overfitting. Then you go back to you need to maybe get more data and do adjust the hyperparameters, do the training again, and then you run it through again to see whether or not there's overfitting. So the output of the process is actually a trained model, but the trained model may or may not be good enough for deployment. So you do need to test the trained model using this process to just check whether it's overfitted or whether it's underfitted or there's any other instability or defects in the model that actually prevent you from actually deploying it. The output that you have from the process is already present here at this stage, just that this is actually just a QC. Now, once it is okay, you actually do not need to use the rest of the data, like the data for the test data, the training data. You actually do not need. All you need for actual deployment is the model itself, right? Because the model just like the Big Girl movies example, is already the trained program. It's the automatically generated program that can create the result that you want. So you don't actually need the training data for model deployment. You just need the trained model itself. So once it passes the QC stage, you can actually just save the model and use that in your server to actually deploy into the actual environment. So this is another diagram from this Thai professor. He calls himself the data professor. So it just shows the same process, but in a format that is more similar to what we will see in the Azure Machine Learning Studio, top to bottom flow. So the initial data comes in at the top. You need to do some data cleaning to get your clean data set. Among the other things that you need to do will be to do some exploratory data analysis. So you need to do various plots and visualization to just check for things like outliers, data that is very far from the normal range, data that's missing, right? Because if you don't actually clean up this data, you will find that you will distort your results because missing data is often treated as zero. So imagine you have a column called age. If there's a missing data there, you'll be treated as a zero rather than being treated as any normal range of age. So if you don't do anything, you just made everybody a baby at age zero. Right, so typical data cleaning for this kind of missing values would be either you drop the whole row, because if you have many rows of data available, you can afford to drop some rows that have missing values. But if you are not able to drop because you don't have sufficient data, then the more logical approach is, rather than not doing anything about it and making everybody a baby, change the value to the average value. The average value of the age is more likely to be a correct value than the age of zero, or age of 200 if somebody actually enters another value, not missing, but it's outliers. Super large value that's actually far beyond the normal range. Right, so same thing for outliers, you either drop the whole row or you may want to replace the original value with a more reasonable value that you can deduce from either the median or the mean, the average. Now the data is structured data. So this is supervised learning. So the Y here is actually the label, right? The correct answer associated with the input variables. Each of these input is also called a feature. So in machine learning, the input variables are also called input features. The output variable is called the target variable or output variable, or sometimes called the class or label variable, right? So the Y is present for supervised learning. For unsupervised learning, you only have the X, no Y, right? The label is not present. Now the data then is actually split into two. One is the training set, and then the other remaining randomly sampled is the final exam questions, the test set. Now this 80-20 is often shown in many textbooks and also websites. It is just a ballpark figure. It's not a cast in stone. It doesn't mean that every time you set a training set, you must only pick 80%. That's like the magic number that you must use. No, it's not the case. Okay, it's just a ballpark figure. You can use 79, you can use 78, you can use any number, but typically you want to use set aside more of the data for training, because that is actually your valuable data. You don't want to use all your training data just as a QC, right? Because this, once you set it aside as the test data, you're not supposed to use it for training at all. It's supposed to be hidden from the algorithm. The key to making it work is that if you have a leakage of your final exam questions, then whatever you're doing to train, then the so-called QC check that you do at the end is just utter rubbish, right? It's just fooling yourself. You may do very well, but that's because you have leaked some of the questions from the test set to the training data. So it's very important that you have to keep these two completely separate. Okay, you cannot afford to leak data from your test set into your training set. The leak can be direct like this, but it could also be by tuning. You tune using the test set. So in some sense, there's some information leaked from the test set into the training set if you do the tuning using the training, which is why people have another set called the cross-validation set. Okay, so that's used for tuning, for adjusting the hyperparameters. So you do not use the test set for your adjustment of hyperparameters. The final output after passing various learning algorithms through it is actually the trained model. And as a final check, we just pass the test set to it to see what are the values that are predicted, and we can various metrics such as accuracy for classification and mean square error for regression. So the metrics or the measures you use, it depends on whether it's a classification problem or regression problem, or if it's unsupervised learning, there will be other metrics that you can use. Though for unsupervised learning, it's a little bit more subjective because there are no standard objective measures because there's no prefix answer, right? Unlike there's no why, you are only detecting the pattern. The pattern that you detect may not be related to any real business case. So that's one of the challenges for unsupervised learning. But for supervised learning, as in this, what shows shown in this diagram, there are clear metrics to measure it. Okay, so this is once you've created the model, this model, as I mentioned, this is the golden nugget that you want to actually use. It's already the program that's learned everything it needs from the data. So you can actually use that in the actual application itself or deploy in the actual application itself. So let's say, okay, so in Azure Machine Learning, after you do the training evaluation, you publish as a web service, you will then have the production web service. Another way to look at it is that I have my trained model. I've actually done the training using my training data. I finally got a model that's good enough to be used. I would just put this model in my server, my web service. And when I actually want to use the model, all I need to do is present it similar data to what it was trained with. Now, this training data can be removed. Once you have actually deployed it, you don't need to put the training data in the server anymore. The model already knows how to do everything it needs to do. Right? It doesn't need the training data anymore unless you want to use that original training data to supplement with new data to do some retraining. Right? If you are actually just going to do the use the model, just put it on the server. Your application will send the image. Let's say it's the cat classification model. I will send the image of the animal with the pointy ears, which is similar to the original training data with the labels, and then the predicted label will come out. And in this case, it correctly predict that the label for this image should be cat and not dog or something else, right? So that's actually how the model is actually used after it's been trained and created. So in the AIoT, in the artificial intelligence of things, very similar. The trained models may be trained in the cloud, but when it comes to this inferencing or running the model, it can be very fast. Actually, what's very intensive in terms of computation is the training process. Typically, training, you can't carry it out in the edge device. You cannot carry out in your AIoT device. You have to carry it out on the server in the cloud itself, which we'll talk more about in the last module 4, we talk about various cloud services. The cloud services will be needed for the training purpose, right? For you to build your model for the millions and maybe thousands of examples in your training data. But once you have actually built the model, this trained model can of course run in the cloud because it has sufficient computational power. But an alternative is to actually push this model down to your device, because the model may not need a lot of computational power to actually run. This process of running is what we call AI inference or AI prediction. The AI, not the training, but the AI inference or prediction process can be executed on the edge device. And we will see more of this being done as we move towards things like smart cameras, right? So not only is the camera just able to capture images, but if you can pass the trained model to it, you can also use the trained model to do some prediction so that it doesn't just send the raw data, but it actually can do some prediction or inferencing using the trained model on the data itself on site without having to send it all the way back to the cloud. That really cuts down the amount of processing you need and also reduces the latency or reaction time in the whole process. So I gave the earlier example of a fire alarm, right? So if you have a fire alarm, you definitely want the fire to be detected rather than just sending lots of pictures of flames, right? And waiting for the cloud to actually detect that, hey, these are flames, so therefore there's a fire event. So you can do it at the camera itself, which is actually sitting closest to where the flames are occurring. That would be ideal. Okay, thank you for your attention. So actually we come to the last slide already. And there are some references here for you to take a look at for the various definitions of deep learning, machine learning. So I hope this set of videos will help you to clarify important question, what is AI? How is it related to machine learning? And finally, this new area of machine learning called deep learning, how is it useful for handling unstructured data? So thank you for your attention. And in the next set of videos, I'll talk a little bit more about the process itself that we just went through. I'll show you a practical example of that using a cloud tool and also some use cases for AIoT in different sectors. Thanks.